Now, if you want to use the IO pin as an interrupt line, then you need to configure the pin as an input port. So here's the pin, and if you have to configure it as an input to use it as an interrupt pin. So this read line will go and trigger the interrupt. So that's something that you need to be careful about. Now going forward, so we will see how the input, if the pin is configured for input, how it looks. So the output driver is disabled here. Output buffer is disconnected and the Schmitt trigger here is activated. That is, the input connection is made, but this is high impedance. So this one is high impedance. We should remember that for input. So it's high impedance. And if we do not have a pull up or pull down here, or we do not provide an external pull up or pull down to this pin also becomes a floating pin if we configure it for input. So we need to have a pull up and pull down for the pin to be in a well-defined state. So the Schmitt trigger is activated. The pull up and pull down resistors are activated depending on the value in the GPIO-X PUPDR register. So depending on that, we make it either a pull up or a pull down, and the data present in the IO pin are sampled into the input data register every AHB clock cycle. So AHB clock cycle would mean if the AHB clock cycle is 84 megahertz, say, so the sample rate is going to be, sample time is going to be every 1 over 84 into 10 to the power of 6 seconds. Okay, so this is going to be the sampling time. If it's 100 megahertz, the sampling time is going to be faster. It's going to be 1 over 100 into 10 to the power of 6. Okay. And a read access to the input data register provides the IO state. So if we read into this register, it will tell me what data I have. For the output configuration looks different. In the output configuration, we have both the blocks enabled. Now you might wonder why the input driver is also enabled if we only need the output part. That is required because if we need to read the value of the output pin, that is whatever value we output through the pin, if we want to read it back, that's the reason we have the input driver also enabled. Now when the output buffer is enabled, it can either be enabled in the open drain mode or push-pull mode. We saw that previously. That is how the open drain mode looks like and how the push-pull mode looks like. So in the open drain mode, a 0 in the output register. So if we have a 0 in the output control register or output register, okay. So let's say if we have a 0, it activates the NMOS. So when it is a 0, it activates the NMOS here. Okay, and then we know that in the open drain, it's just shorted to the ground. Okay, and leaves the port in the high impedance because the PMOS is never activated. And if we make it a 1, okay, then the NMOS is switched off. Okay, it's in the high impedance state. In the push-pull mode, a 0 in the output register activates the NMOS. So 0 activates the NMOS and a 1 activates the PMOS. So this is the push-pull configuration. So there is a difference between the open drain mode and push-pull mode. Here we are activating only the NMOS here. Okay. And here we are activating the PMOS. And the Schmitt trigger is also activated. And if you have any doubt about this setup, go back and have a look at the open drain and push-pull configuration separately. This will become very clear to you. Since we have dealt with those circuits separately, it should not be a problem. Now the Schmitt trigger input is activated we have the weak pull up and pull down resistors activated or not, depending on the value of the GPIO PUPDR register again. So here it's a weak pull up pull down. It depends, because if it's an open drain, we have to have a pull up pull down, and if it's even if it's a push pull, then also we need to, because push pull is sourcing and sinking current, that needs an that is the one which is used for UART and SPI. Okay, so let's go back to the push pull configuration once and have a look. So, and as you can see, the output of the push pull always needs to have a resistor to limit the current to the specified value. Okay, so here it's not a pull up pull down for the push pull, but you need to have an output. The output current has to be controlled here, and the weak pull up pull down could do that job. And the data present is sampled in the input register every AHV clock cycle, like we saw in the previous slide. Same here. The read access to the input data register gets the IO state. So if you do a read access, you will know what the IO state is. That is, whatever you have output, the same should be read in as input. Read access to the output data register gets the last written value. So whatever you wrote last through the output unit is can be read back. If you read, then the last written value is read out. Now, alternate function configuration means you are using this for, say, like we discussed, say you want to enable the SPI, serial peripheral interface, for this particular unit, then you use the alternate function configuration. Now, alternate function configuration would mean that the IO registers will be disabled. The input data register will be enabled still, but the output data register is disabled. So whatever you output, the alternate function output, whatever you have, is through here, through the output control. Okay, and the input data is read back to the alternate function input, because it also needs to read back the value. For example, it might say SPI, it might be sending some data, or it might be receiving some data, right? So when it receives data, it has to read the data back. So this is the alternate function input, and this is the alternate function output. This unit is disconnected, but you can actually read the data. So output buffer can be configured as open drain or push pull. That is even in the output configuration. The output buffer is driven by the signal coming from the peripheral, the transmitter, enable, and data. So it's coming from the peripheral. It is not coming from these registers now. Okay. The Schmitt trigger input is activated. The weak pull up and pull down resistors are activated or not, depending on the value of the GPIO PUPDR register, which is the same. And then the data present on the IO pin are sampled into the input data register every AHV clock cycle, which we have seen previously also. And a read access to the input data register gets the IO state. So if you want to know what is on the line, then you can read this value. But then otherwise, the entire operation, it takes place over the alternate function output and alternate function input value. We don't generally use the IO here. Here the output IO is anyway disconnected. Input IO we may or may not use. It's all on the alternate function. It's all being controlled from the alternate function block. Coming to the analog function configuration, the setup is a bit different. That is, the first thing that we see that is different from the previous configuration is that the Schmitt trigger is turned off. Okay? That's one thing we see. So we cannot read anything in the input data register, and the output unit is also cut off. So we have an analog input coming in through here, and this one goes into the circuit. So the output buffer is disabled. The Schmitt trigger input is deactivated, providing zero consumption for every analog value of the IO pin. Okay. So we cannot read anything from the analog IO pin. So that is completely disabled. Okay. The weak pull up and pull down resistors are also disabled. read access to the input data register gets the value 0. So if you try to read, you get a value 0. In the analog configuration, the IO pins cannot be 5 volt tolerant, because even though you have the protection diode, it is still not 5 volt tolerant. So for analog input output, if you are working on analog inputs, it cannot exceed 3.3 volt in our case. So if you are feeding analog signals through the say your ADC pin, you have to maintain 3.3 volt logic level, not 5 volt logic level. So you have to be careful about that. Now let's go through the GPIO registers. Now this segment is very important, because any peripheral that you access from the microcontroller will be using input output pins, which are part of GPIO. Now the addressing, as I mentioned earlier, there are multiple data sheets and reference manuals that you need to go through whenever you have to learn about your STM32 microcontroller. So this is the reference manual, which will have in chapter 8 for this version of the reference manual. We have the information on GPIO registers. So we have already covered the GPIO pins as to what the different about the different configurations of the pins and so on. So moving on, the first register that we have is GPIO port mode register. But even before that, let us talk about the address of the GPIO base. Now the peripheral base is the base address of your AHB1 bus, and for GPIO port A, it is at offset 0. So ideally the address of GPIO port A is 40020000. Okay. Now if you need to know the base address of the ports, you could do it in a few ways. One of them is to actually go to a different place in the reference manual itself and look at the base addresses for your AHB buses. There's another way, that is to have a look at the memory map, that is a CMSIS memory map. So the way it is being laid out is it's not difficult, but you have to go back a few steps to really know which base address that the particular GPIO is on. For example, if you look at the memory map header file, it says GPIO base is AHB1 peripheral base plus all zeros. So we have to know, or we have to find out what is AHB1 peripheral base. So let us do that. We'll do find, and we see that the AHB1 peripheral base is again 20000 UL. Okay, so this is the AHB1 peripheral base, and AHB1 peripheral base is again peripheral base plus this. So let's look for peripheral base. Peripheral base is here, that is 4 with 7 zeros. So AHB1 peripheral base is 4002 with all zeros. Okay, so that is your AHB1 peripheral base. So if you need to know GPIO A base now, so GPIO A base is 4002. So let's check this. So we saw this once. Let's check it once again. Let's do Control F and find. So GPIO A base is 40020000. That is 4002 with 4 zeros. So this is the GPIO A base. Now GPIO B base is AHB1 peripheral base, which is 40020000, and we add 400 to that. So that will be, so that is the GPIO B base. So this is how you calculate the base address. So it's not directly written anywhere. So it is 0x4002, okay, 0400. So this is the GPIO. So you don't have to do this calculation as such. It's all here. So if you just access that particular GPIO base, the header file is going to take care of it. But if you really need to know where the base, what is the base address of that particular GPIO register, this is how you do it, just for your knowledge. Now, coming to, so I've just written that down here. That's a peripheral base is AHV1, and that's this address, and every GPIO has a separate peripheral base with respect to AHV1. So the first register that we see is that GPIO port mode register, okay, and the name of that, and it is called GPIO X MODER because every port has its own port mode register. So port A has a port mode register, so it is GPIO X. X stands for which port. So port A is GPIO A port mode register, port B is GPIO B port mode register, and so on and so forth. Okay. Now this is the first thing that you need to. Okay, so even before setting everything, suppose you are, we will see one GPIO code here with the discovery board after this. But nevertheless, even before this, you have to enable the port first. But after enabling the port, you have to set the mode for that particular port. Okay, and so this is the register. So there are as many registers as there are ports here for this particular board, and there are, if you see, there are 16 fields here. Each field is of 2 bits. So this is for port A. So if there are 16 pins, there are 16 fields here. So this is covered by 132-bit register only. Okay. So this is, say, if you want to set port A0 pin 0, this is the place where you set it. Port A0 pin 1, pin 2, pin 3. It goes on like this to port A0 pin 15. So 00 is the input state. So if you want to configure a pin as an input, you need not even touch this register. Automatically it is set to input. But if you want to set it to output, then you need to set any of these bit fields, whichever you need. For example, you want pin 14 to be as output, then you have to set 01 there. 10 is for alternate function mode. Alternate function mode, we spoke about alternate function in our when we were discussing the GPIO functionality. Alternate function pins are where the GPIO is able to provide you with a different functionality like UART or SPI. So at that time, the GPIO pins are not going to be, the GPIO function is going to be replaced with the digital function for that pin. That is, it might be, as I said, it can be any function. It could be USB also. And then you have the analog mode, and we talked about analog mode. Analog mode is if you need that pin to function as an analog input. Say it's an analog input going into your analog to digital converter. So that time you have to 11 is the configuration for analog mode. So this is the GPIO port mode register. So second is the GPIO port output type register. Now again, you have the offset is 0x04. That is, if it is 40020000, 40020004 is the address of this particular register, and it configures that pin either as a push pull or open drain. So 0 is push pull, that's a reset state. If you make it 1, it becomes open drain. And so we know that, push pull, say if you want to if you want to set your pull up and pull down using an external resistor or the internal weak pull up pull down resistors for any application, you can use open drain. Otherwise you can use push pull. So that is something that is configured using this particular register. So for us it's 0 PA0. So this is the place where we are going to configure that. So, and just when we are going through this, remember what we learned in the previous sections, that is about the diagrams that you saw. Okay, so this actually is configuring the registers so that remember the diagrams that you had for different output configuration like push pull and open drain. Remember the transistor diagrams that we went through as to what push pull and open drain is. So this is just configuring them. So relate to that when you go through this part, so it becomes easy for you. Then you have the GPIO port output speed register. We will not touch this. By default this is 00. So, and it is low speed. We can configure it for different speeds, medium, fast, high speed, and so on. And if you want to do that again, there is a you can go to the product data sheet. Product data sheet is a particular microcontroller data sheet, and it will actually tell you for each value what is going to be the output speed of the GPIO port. Okay, output speed would mean how fast can you wiggle the data in the pin for it to faithfully output that particular data. Okay, if there is too much delay and you wiggle the data too fast, then of course you will not get the right data out of the pin. Okay, so the rise time and the fall time is all managed through this. In case you want to see that, where you can find it, just search for the string in the processor data sheet. So let's do that. So let's search for that string in the processor data sheet. I've already put the string here. So if you do that, this is the place where you have all that information. That is, for this value which you saw here, these values 0, 0, 0, 1, 1, 0, 1, 1, what are the what is the max speed you can get? So for us it's 0, 0, and it says what is the load capacitance for and for that load capacitance. So our VDD is 3.6 volts for our particular discovery board. So it's going to be of our UART speed is going to be 4 megahertz. Okay. Similarly, if you want make it 0, 1, then the speed increases. 1, 0, speed goes even higher, and so on. Okay. So we'll not bother about this for our course, but it is good to know. So in case you are trying to write an application where you need you are doing some writing some application where you need the port to respond faster, then this is the place that you go to. Then you have GPIO port pull up pull down register. Now this is again we spoke about the weak pull up and pull down resistors for in our case. This is the place where we set that. For example, for us, say it's port A0. If we if we don't need any pull up pull down, then the setting is 0. If we set it to 0, 1, then it's a pull up. 1, 0, it's a pull down, and 1, 1 we don't set. 1, 1 is reserved. So setting that value here makes it a pull up pull down, and so on. Okay, no pull up, no pull down, pull up pull down, and it's reserved. Then you have GPIO port input data register. So this is the port where you read the data that is coming to the port. So one field for each pin. So we will be reading, say, port A0 value. Okay. So when I say port A0, this is for the the user button that we have on the discovery board. So that's connected to port A0. So we'll be reading the port A0 value. Okay. And this is read only. You can only read values. You cannot write into this. Okay, and they contain the input value of the corresponding IO port. So you will have the entire IO port populated in the sense this register will be will have. So when we use the user pin here, probably all of these values will be zeros and only this value will be 1. We are only concerned with this value. Then you have GPIO port output data register. That is whatever value you want to output. So for the LEDs that we are going to blink, we are going to use the output data register, one of the output data registers from where the LEDs are connected for the discovery board. Okay. So if you want to see where the LEDs are connected, then go to the discovery user manual, and I've just made some notes where you have the LEDs. Let's see where the LEDs are connected. So as you can see, the LEDs are connected in port D, 12, 13, 14, 15. Okay. So we have to, that time we have to go to port D and output whatever port we want to output the value as. We have to we have to put 1 in that particular field, and that LED will glow. Okay. So this is your this is the GPIO port output register. So we are not talking about atomic bit set reset here, like individually set and reset by writing to the GPIO BSRR. We are not doing that. We'll follow the conventional method. So this is the output port data register. So again, you have one set of register for every port: port A, port B, port C, port D, port E, port F. Okay. So wherever you want the data to be output, you write here. Then you have a GPIO port bit set reset register. We will not use this. Okay. And then you have port configuration lock register, which actually locks the ports. That is, until a reset, that particular port is locked. Okay. The register is used to lock the configuration of the port bits, and when a correct write sequence is applied to bit 16 LCKK, the value bits is used to lock the configuration of the GPIO. During the write sequence, the value of this must not change. When the lock sequence has been applied to the port bit, the value of this port can no longer be modified until the next MCU or peripheral reset. So you can lock a port using this particular register. So we'll not do that, but you can go through it. So in case you have some applications where you need to work on the lock bits, this is the place where it's the GPIO alternate function low register and high register. So every GPIO pin, as we talked about, has an alternate function. Not every, but most of the GPIO pins have an alternate function. So every field, so here you can see every pin has 4 bits. So bit 1, bit 2, bit 3, bit 4. So since every pin has 4 bits, there has to be 2 registers, low and high, to represent a particular port. And that is what is happening here. So say for port A or port D, for us, we need to configure port A and port D. So in our case, we don't need to do any configuration because there is no alternate function here. We are directly using it as an input and output port. But suppose you need to configure this for an alternate function. For example, you want to enable your UART or SPI or anything for that matter, digital function. You need to come here, and for that particular pin, your alternate function is going to be like this. So 0 is 0, alternate function 1, 2, 3, 4, 5, 6, 7, 8 to alternate function 15. Now, how do you find out what is the alternate function that you need to put? For example, you want to use UART or you want to use USB. How do you know which alternate function to put? So for that, you need to go to the microcontroller datasheet. And in the microcontroller datasheet, you have to go to the alternate function mapping. So when you go to the alternate function mapping, this is what you see. So for every pin, so you can see PA0, PA1, PA2. So it goes down like this. For this is the data sheet for this particular controller. Okay, every controller is going to have a separate data sheet. So we have port A2E and port H0 and H1, and port A to port E has alternate functions. So every alternate function will be in its own column. For example, port A has timer 2 and timer 2 channel 1, timer 2 ETR as alternate function 0, timer 5 channel 1 as alternate function 2, USART2 CTS, that's a CTS pin as alternate function 7, alternate function 15 is event out. Okay. Similarly, PA1, okay, you can SPI4, MOSI, UART2, PA2. So all the pins alternate functions are listed here for this particular controller. So you can see that. So you have to go to that particular pin. For example, if you want to work on USART or UART2, you have to search for that. Okay, come down, and then you see that the alternate function, the TX and the RX, is for port D5 and port D6, and you have the values here. That is, these are the two ports that you need to configure, and your alternate function is going to be alternate function 7. So you have to come to this register, that is, you have to come to the alternate function register, and you have to set that value. So lower register and higher register, this is for the lower 8 pins, and this is for the higher 8 pins. So 5 and 6 that we saw here, suppose the 5 and 6 that we saw here, PD5 and PD6 that we saw here, TX and RX, okay, we'll have to, so let's see where the 5 and 6 are. So we have, so 0, 1, 2, 3, 4, 5 and 6. So it is in the low register only, because 5, 6 it goes up to here. So 5 and 6 here we have to set the alternate function as 7 and 7. 7 means 0, 1, 1, 1, 0, 1, 1, 1. And thus, and the moment you set that, this particular pin, these two pins are going to act as USART2. Okay, and so on. So any other alternate function that you need to set, you need to do it in a similar fashion. Okay, so for USART1, say if you want to set SPI, so you have to go to PB3 and PB4 and so on. Okay, so this table is very important for you. Have a look at this table. In case you don't follow, then let me know. Every row is one pin, and every column is the alternate function that it supports. Okay, so USART6, and then this is the and this is the column for, say, USART2. So alternate function 7 is for, say, USART2 for whichever pin that supports it. So this does not move. For example, so this is something good for you. That is, for timer 1, timer 2, it is all alternate function 1 right across all the pins. So you don't have to worry about having to. So timer 1 or timer 2, say for port A or port B or port C, it is for everything, it is alternate function 1. Similarly, it goes on like that. So setting a timer for different pins is not a different alternate function number. It's the same number. Okay, so just keep that in mind. It is easier for you to remember. You don't have to remember this. I mean to say, remember this thumb rule, so that it's easier for you to set the alternate function. Okay, moving on. Then you have the alternate function high register, because since these are 4 bits per field, you need 2 registers to represent it. And then we have the register map. So these are the GPIO registers that you need to know about when you do some GPIO settings. So now we will, in the demo, we will have a look at a simple input output port setting, and we will see how to configure the push button and the LEDs for normal GPIO. It's not an alternate function, it's normal GPIO functionality. So we'll go through pull up, pull down configuration and everything there.